What's up, my stat stars? Welcome to the AP Statistics Unit 8 Summary Review video. Unit 8 is all about chi-square tests for categorical data. Now, before we dive too deep into the topic, let me remind you of two things. First, of course, this is just a review video. I try to go over all the main aspects of a chi-square test, but there's lots more teeny tiny details that you should be learning in class. But again, I do try to hit the main points to make sure you remember everything. The second thing is open up the Ultimate Review Packet for AP Statistics and get out that Unit 8 study guide. That Unit 8 study guide is filled with tons of problems, tons of practice that you can apply all of the concepts we're going to learn in this video to. So please check out that study guide. It's going to really help make sure that you practice all of the skills that you're about to review. All right, let's dive right into the material. A chi-square test is used for counted data that comes from a categorical variable. We're not talking about proportions here. We're not talking about means here. We're talking about counts of data. Like 13 people were counted to like blue, 15 people were counted to like red, and 26 people were counted to like yellow. That's an example of counted data across a categorical variable of what's your favorite color. This is the type of data that a chi-square test is used on. Now, how do you recognize in a problem that you need to use a chi-square test? Well, typically you're going to see counted data from a categorical variable with 3 or more different categories. Or you might see a two-way table that has 2 categorical variables with multiple categories for each. Anytime you see a table like that with counted data and you're asked to conduct a significance test, you're typically going to need a chi-squared test. Now, there are 3 different types of chi-square tests. There's a chi-square test for goodness of fit. That is used for one categorical variable with multiple categories to it. Then we have a chi-square test for independence, or also known as a test for an association. There you're going to see a two-way table where you're trying to determine if there's a relationship or an association or independence between those two variables. And lastly, we have a chi-square test for homogeneity, which also involves a two-way table with 2 categorical variables. Now, regardless of which one of these tests you're going to use, all 4 have a very similar structure. Step 1 is to name the test and write the hypotheses, the null and the alternative. Typically here you're going to use words to write those hypotheses. The second step is to check the conditions and calculate your expected values. The third step is to calculate your total chi-squared value and then calculate the p-value from that chi-squared total. And then the fourth step is to make your conclusion. This is where we're going to compare our p-value to our alpha level to determine if we're going to reject the null or fail to reject the null hypothesis. First up, let's talk about a chi-squared goodness of fit test. A chi-squared goodness of fit test is a statistical test used to determine whether observed categorical data matches an expected distribution. Here's an explanation of how a chi-squared goodness of test works. First, we have to make sure that we understand this setup. In a chi-squared goodness of fit test, we start with a categorical variable that has different categories or levels. For a chi-squared goodness of fit test, there's only going to be one categorical variable with multiple categories or levels to it. Now, we have an expected distribution of frequencies for each category based on some theoretical or assumed distribution, meaning in the problem that they're going to tell you what the expected distribution for that categorical variable was. This could be a specific hypothesis or an expected distribution based on historical data or theoretical expectations. Now, here when we're formulating hypotheses for step 1, the null hypothesis is that the observed frequencies in each category match the expected frequencies according to the specified distribution. Basically, the distribution amongst the categories is what we expected it to be from what the problem said. The alternative hypothesis is that the observed frequencies in at least one category do not match the expected frequencies. In other words, the distribution amongst the categories are not what was expected. Now, in order to make a statistical inference for a chi-square test for goodness of fit, we must check 3 conditions. This is going to be step 2. First, of course, the sample has to be random to avoid bias. Second, the size of the sample must be less than 10% of the population so we can assume independence. And third, there must be 5 or more expected counts in each category. This is why in step 2, after we check our conditions, we actually have to find the expected values based on what the problem says. That way we could check that third and final condition that we do have 5 or more expected counts in every category. Now, how do you get those expected counts? Well, you got to read the problem. Sometimes it'll say the distribution of the categories are all equal. So you simply take your total number of observations and you divide by how many categories because they're all supposed to be the same. Or, like mentioned, we'll give some historical or theoretical distribution of what is supposed to be there. And from that distribution, you have to calculate your expected values. Once you have your expected values, you could then go ahead and calculate your chi-squared value. Now, the chi-squared statistic is using this formula. You take the observed value in a category minus the expected value for that category, square that difference, then divide by the expected. Now, you're going to do that for every single category. Observed minus expected squared, divided by expected, repeat, repeat, repeat. Once you have each chi-squared value for each individual category, you add all of them together to get your total chi-squared statistic. Then we could use that chi-squared statistic to generate our p-value. Now, what we're going to do is we're going to use technology to generate that p-value. So we're going to use a chi-squared CDF on the TI-84 calculator. Now, when you use a chi-squared CDF, the first thing you're going to do is enter in your chi-squared value as your lower value, and then your upper value is going to be something like 9999, some really, really big value. But you're also going to need your degrees of freedom. So how do you find the degrees of freedom for a chi-squared goodness of fit test? You simply take the number of categories that you have minus 1. So if you have 5 categories, minus 1 is 4 degrees of freedom. We do not use the size of the sample like we have done in the past. Please keep that in mind. It's a big thing that a lot of kids do wrong. It's the number of categories minus 1 for your degrees of freedom. Once you have all that entered into chi-squared CDF, you could generate your p-value. An interpretation of the p-value for the chi-squared test for goodness of fit is the probability, given the null hypothesis and probability model are true, of obtaining a test statistic as or more extreme than the observed value. The p-value can be found using technology such as the TI-84 calculator. We can use chi-squared CDF, which requires the chi-squared value and the degrees of freedom. Finally, we have to make our decision. This should sound very familiar to what we've done in the past with proportions or means. If the p-value is less than our level of significance, which is typically 1 or 5%, we will reject the null. This means that we do have statistically significant evidence that the alternative hypothesis is correct. Or if our p-value is greater than our significance level, again, typically 1 or 5%, we will fail to reject the null. This means that we do not have significant evidence that the alternative hypothesis is true. We do not claim that the null hypothesis is true. We just do not have enough evidence to say the alternative is true. Keep that in mind. The test is always about the alternative. We're never checking if the null is true. We're simply saying, do we have enough evidence that the alternative is true, or do we have a lack of evidence that the alternative is true? Those are the 4 pretty simple steps to conducting a chi-squared test for goodness of fit. In summary, the chi-squared goodness of fit test allows us to assess whether observed categorical data fits a specified distribution, providing insights into the adequacy of the theoretical model or hypothesis under consideration. All right, let's dive into a quick example so we could see how all of those steps work out. All right, in this example, data was collected from a random sample of 450 adults in Ohio, and it shows the following breakdown of eye color. So we have a sample of 450 people, and we identified the counts for blue, brown, green, hazel, and amber eye color. Now, researchers for a long time believed that nationwide the proportion of eye color are as follows. So this is the historical or theoretical data distribution that we would expect. 10% blue, 78% brown, 2% green, 5% hazel, 5% amber. So does our sample provide convincing evidence that the proportions held by researchers for the nation are no longer valid in Ohio? All right, so step 1 is going to be naming the test. This is only one variable here, eye colors. This is definitely going to be a goodness of fit test. We basically want to see how good does our data fit with what was expected. Because if it's too far off, that's when we're going to reject the null and go with the alternative. So the next step is to identify the null and alternative hypotheses. Now there's two ways we could do this. We could do this with words, where the null would be the distribution of eye colors for Ohio adults are consistent with what was expected from the researchers' claims for the nation. And the alternative is the distribution of eye colors for Ohio adults are not consistent with what was expected from the researchers' claims for the nation. Basically, your null and alternative hypothesis are the exact same sentence, but the alternative has the word not in it. So the null is that everything is the way it historically was supposed to be, and the alternative, what it was not the way it was historically supposed to be. Now, we could also use symbols here, but I think writing it in sentences is actually a little bit faster, but we could use symbols and numbers here. So the alternative would be the individual proportions for each eye color: blue, brown, green, hazel, amber, giving those proportions that we were told were historically true. And the alternative is that at least one of them is incorrect. All right, next up is checking the conditions. The sample, of course, has to be random to avoid bias. We also have to assume that 450 adults is less than 10% of all adults in Ohio, so we can assume independence. I think that's a pretty safe assumption. And the third condition is that we need to have 5 or more expected counts in every category. So now it's time to calculate our expected counts. Now, to get the expected counts, we're going to use the percentages that were given. For example, we were told that 10% were supposed to be blue. So we're going to take 450 adults, that was our sample size, and multiply it by 0.10 to get 45. So we expected 45 to have blue eyes. That's that 10%. Then we're going to repeat that for the brown. 78% of 450 was supposed to be brown eyes. That's where we get 351. So now we want to make a nice chart here. We already have our observed values from the chart. 40, 370, 5, 20, and 15. But now we're calculating the expected values based on the given proportions. 45 blue, 351 brown, 9 green, 22.5 hazel, and 22.5 amber. All right, all of those values are 5 or more, so that third condition checks out. Now it's time to actually calculate our chi-squared statistic. So again, we're going to take each observed value minus its expected value squared divided by the expected. Once we do this for each individual category, we will then add them all together. So here's all my work for that. This is where it does take a little bit of time, a little bit of math work. Make sure you're being very careful in keeping that numerator in parentheses and then squaring it before dividing by the expected value. So I added up all of my chi-squareds and I got a chi-square total of 6.14. Now I'm going to go ahead and use my calculator to calculate the p-value using chi-squared CDF. The lower value is going to be 6.14 and my upper value is going to be 999, acting like a really big value towards infinity. But I also need degrees of freedom. So I had 5 categories: blue, brown, green, hazel, and amber. 5 categories minus 1 is 4 degrees of freedom. Typing all that into my calculator, I get a p-value of 0.1889. Now it's time to make my conclusion. Now, since my p-value of 0.1889 is greater than 0.05 or even 0.01 if you use 1% for your level of significance, I'm going to fail to reject the null. There is no significant evidence the distribution of eye colors for Ohio adults are not consistent with what was expected from the researchers' claims for the nation. So basically, we're not saying that those numbers that we were given that are true for the nation are guaranteed to be true for Ohio, but we just do not have the evidence to say that Ohio is different than that. At the end of the day, it might be, but we don't have the evidence to officially say that. So the distribution of eye colors for adults in Ohio is not significantly different than the distribution for the nation as a whole. The eyes of Ohio are probably no different than the eyes of the nation. Yes, we saw some slight differences, but nothing too significant for us to officially say Ohio is different than the rest of the nation. All right, so those are the 4 steps that we ran through pretty quickly. It's not too bad to conduct a chi-squared goodness of fit test. The next type of chi-squared test is a chi-squared test for independence or a test for association. This test is used when you have 2 categorical variables and you want to determine if they are independent of each other or if there is a strong association between them. The basic process looks like this. We first set up our null and alternative hypotheses. The null hypothesis assumes that there is no association between the variables, while the alternative hypothesis suggests that there is an association. The test involves calculating the expected frequencies for each cell in a contingency table, also known as a two-way table, under the assumption of independence, and then comparing these expected frequencies to the observed frequencies using the chi-squared statistic. If the chi-squared statistic exceeds a critical value based on the chosen significance level, then the null hypothesis is rejected, indicating a significant association between the variables. Now let's run through the 4 steps. They're going to be very similar to a goodness of fit test, but a little bit different, especially in the hypotheses and the construction of the expected values. So the first step is really getting those hypotheses. The null hypothesis is that there is no association between the two variables. Just make sure in your sentence you're using the actual context of the problem. And the alternative is that there is an association between the two variables. Now the next step is of course checking the conditions. The sample must be random to avoid bias. The sample size must be under 10% of the population. In every expected count also must be 5 or greater. So let's talk about how to get those expected counts. In a two-way table, to get the expected counts for each cell, you take the row total for that cell times the column total for that cell divided by the grand total of the entire table or your entire sample size. So once again, when you are trying to pinpoint what the expected value in a specific cell is, just look at the row total times the column total divided by the grand total, and you'll get your expected values. And make sure that all those expected values are 5 or more. Once you've calculated all those expected values, you have the observed values from the original two-way table. Now you have the expected values that you found for each count. Now, those expected values are on the assumption that there is no independence. By calculating the expected values in the way that I described, what you're doing is you're determining how many counts of data should be in each cell if there was no association, which means independence. Now we have to find our chi-squared statistic in step 3. So the first thing we're going to do for every single cell is take the observed value minus the expected value all squared divided by the expected. Then we're going to add all of those individual chi-squareds together for each cell to get our total chi-squared value. Next up comes finding our p-value, which is the probability that what we observed or more extreme occurs on the assumption that the null hypothesis is true. Now, the one thing we have to figure out real quick is the degrees of freedom. How do you find the degrees of freedom in a two-way table? Well, what you do is you take the first variable's categories minus 1, multiplied by the second variable's categories minus 1. So let's just say one variable has 3 categories, 3 minus 1 is 2. The other variable has 4 categories, 4 minus 1 is 3. So we take the 2 times 3 for 6 degrees of freedom. A little bit confusing, but just remember you got 2 variables, so you got to take the first variable, how many categories do you have for that first variable? Minus 1. Look at your second variable, how many categories do you have? Minus 1. Multiply those 2 results together for your degrees of freedom. Then what you could do is use chi-squared CDF to get your p-value by typing in your chi-squared value first, going to an upper value of 999, acting like infinity, and then don't forget to enter in the degrees of freedom. Now the fourth and final step is of course making the conclusion. So what we're going to do is we're going to compare our p-value to our level of significance, which is usually 1 or 5%. If your p-value is below your level of significance, you're going to reject the null, which in context means that we do have evidence that the alternative is true, which means that we do have significant evidence that there is an association between the two variables. However, if your p-value is greater than your alpha level, then we're going to fail to reject the null, which means we do not have enough significant evidence to claim that the alternative is true. Are we saying for a fact that these two variables are independent? No, not at all. We just don't have enough evidence to reject independence and say that there definitely is an association. All right, that's the basic steps for a chi-square test for independence. Let's look at a quick example. A random sample of 620 registered voters from a large county in California were asked what political party they affiliated themselves with. The two-way table below is the results of the survey. So we have 2 categorical variables. First is what political party do you associate yourself with? And there's 3 categories, Democrat, Republican, or Independent. And then the second variable is your gender, male or female. So we have 2 variables, gender and political party affiliation, and they each have several different categories. So does this data show an association between gender and political party affiliation? So does your gender have a relationship with your political party affiliation is what we're asked. So we want to conduct a test at the 5% significance level to find out. All right, so the first step is those hypotheses. This is going to be a chi-square test for independence, clearly because we have one sample, and from that one sample, we looked at the relationship between two things. We asked the people in our sample, what's your gender, what's your political party affiliation? So the null hypothesis is that there is no association between gender and political party affiliation for registered voters in this county of California. Once again, notice I'm not just saying there's no association, I'm giving the context. No association between gender and political party affiliation. The alternative is that there is an association between gender and political party affiliation. Now, if you don't want to use the words association or no association, you could also use independence. Remember, no association means independence. So the null could be that there is independence between the two variables, and the alternative would be that there is not independence. All depends on how you want to word it. All right, the second step is checking those conditions. The sample must be random to avoid bias. The sample must be under 10% of the entire population. So we assume 620 registered voters is under 10% of the entire population in the county. But we also need to have 5 or more expected counts in each category. So here we go to determine how many expected counts are in each cell. Once again, what we're doing here is we're calculating what should be in each cell if we have no association. So first I got to go cell by cell. So for the male Democrat cell, I'm going to take the row total, 340, times the column total, 372, and divide by the grand total, 620, and I get 204. I'm going to repeat that process for every single cell. So female independent, row total, 280, multiplied by column total, 75, divided by grand total, 620 to get the 33.87. So a little bit tedious work, but you got to find the expected values for every single one of those cells. Now it's time for step 3, and that's actually getting our chi-square statistic and our p-value. So we're first, for every single cell, going to take the observed minus the expected squared divided by the expected. So male Democrat, we observed 176, minus we expected 204, square that value, all divided by 204. Then we're going to repeat that process for every single cell, add all those chi-squareds together to get our grand total chi-squared, which in this case is 136.25. Now to find our p-value. The p-value is the probability that a chi-squared value is greater than the one we got on the assumption that the null hypothesis is true. Now, how many degrees of freedom do we have? Well, for gender, we have 2 categories, male, female, minus 1, that's 1. For political party affiliation, we had 3 categories, minus 1 is 2. 1 times 2 is 2 degrees of freedom. So I'm going to go to chi-squared CDF on my calculator. Lower value is 136.25, upper value is 999 with 2 degrees of freedom, and I get an extremely crazy low p-value, 0.26, lots of zeros there. So now it's time to make my conclusion. I'm pretty confident in making this conclusion since my p-value is so far below my significance level of 0.05. So I will reject the null hypothesis. There is plenty of statistically significant evidence that there is an association between gender and political party affiliation for registered voters in this county of California. In this county of California, if you are a female, you are much more likely to be a Democrat, and if you are a male, you're much more likely to be Republican based on the data from the table. So in summary, a chi-square test for independence is when you have one sample that you ask 2 different variables from, right? So you have variable 1, variable 2, in this case, gender and political party. And then what you want to do is determine, based on the question, is there an association? Are they independent of each other? And that's where we're going to run through this chi-square test. Overall, not too difficult. The work gets a little bit tedious, but it's nice and simple if we want to finally answer that question, is there independence or is there an association between these variables? The third type of chi-square test is a chi-square test for homogeneity. Now, everything about a chi-square test for homogeneity is pretty much identical for a chi-square test for independence. But it is important that you understand what type of tests am I doing? Am I doing a chi-square test for independence or homogeneity, even though the process is pretty much the same? Now, both of them are used when you have a two-way table looking at 2 different categorical variables. Remember, a goodness of fit test is only used for one categorical variable. Let's talk about a couple of the big differences between a test for homogeneity versus a test for independence. Now, the purpose of a chi-square test for independence is that we're used to determine whether there is a significant association between 2 categorical variables in a sample population. Now, the assumption is that the observations are independent, meaning that the presence or absence of one variable does not affect the presence or absence of the other variable. Now, in a chi-square test for homogeneity, the purpose is used to determine whether the frequency distribution of a categorical variable is similar across different populations or groups. So in a chi-square test for homogeneity, you'll typically have more than one sample. You're going to have maybe 2, 3, 4 different samples across 2, 3, 4 different groups or populations. So that's your first categorical variable. Then you want to see if the distribution of a second categorical variable is the same or different across those groups. So the most important difference that you'll see in a homogeneity test, besides how the question is asked, is you'll definitely see 3, 4, maybe even 5 different groups or samples in how another variable is distributed across it. Now, in a chi-square test for homogeneity, the assumptions of the categories being compared across different groups are drawn from the same population or have similar distributions. An example would say, let's say we want to compare the preferences for 3 different brands of soft drinks, brand A, brand B, brand C, among 3 different age groups, 18 to 25-year-olds, 26 to 40-year-olds, and 41 to 6-year-olds. So the chi-square tests for homogeneity would help determine if there is a significant difference in soft drink brand preferences across the 3 age groups. So notice we're not asked about is there an association, we're talking about is there a difference in the distribution of the particular type of soft drink that you like across these different age groups. That's a chi-square test for homogeneity. Now, the other big difference is simply how you write those hypotheses. The conditions, the expected values, the chi-squared, the p-value, that's pretty much all the same, even the conclusion, but it's the hypothesis. So the null hypothesis is that the distribution is the same across the different groups, where the alternative is that the distribution is, well, different across the different groups. That's the idea. We're not looking for an independence or an association. That's obviously an independence test. We're looking for the same distribution or a different distribution across different groups. Let's take a look at a quick example. 3 different random samples were taken, one from middle school students, one from high school students, and one from college students. Students were asked what they preferred social media app was. The results are in the table below. So here we clearly see 3 different groups, middle schoolers, high schoolers, and college students, and we're trying to see if the social media app that they prefer is the same or different across the groups. So the 3 different social media apps we're looking at were Facebook, Instagram, and Twitter. So again, 2 categorical variables. What is your school age, middle school, high school, college, and what social media app do you prefer? Does the data show significant evidence that the proportions of favored social media app is different across the 3 populations? Conduct a test at the 1% level. So again, we're not asking you is there an association or not, because that would be a chi-square test for independence. And there's not just one huge sample where we ask them 2 different things. We have 3 different populations, middle school, high school, college students, and we're trying to look at another variable across those 3 different populations. This is a clear sign of a chi-square test for homogeneity. So step 1 is simply saying that. This is a chi-square test for homogeneity. And then the null is that there is no difference in the distribution of social media preferences across the 3 populations of middle school students, high school students, and college students. Always write that null and alternative in context. But the null is that no difference, status quo, everything's the way it should be. And the alternative is what we're wondering, is there a difference? So the alternative is there is a difference in the distribution of social media preferences across the 3 populations. The second step is checking those 3 conditions. And in that third condition, we got to make sure that every category has 5 or more expected counts. How do you find the expected counts in a 2-way table like this? Once again, for each individual cell, and there are 9 of them, so there's lots of math to do here, but we're going to take the row total times the column total divided by the grand total. For example, high school students that prefer Instagram, row total 200 times column total 370 divided by grand total 570 to get the 129.82. You're going to repeat that process for every single cell. A little bit time consuming, but that's what you got to do. All right, the third step is getting that chi-squared test statistic. So for every one of those 9 cells, we're going to take the observed minus the expected squared divided by the expected. So for example, middle schoolers that like Facebook, we observe 12. We're going to subtract the expected 21.05 squared divided by 21.05, and we're going to repeat that process for every single one of the 9 cells. Add all those individual chi-squared values together to get your grand total chi-squared, in this case 12.589. Now, the other thing we need so we can next find our p-value is the degrees of freedom. Well, there's 3 populations on the left. 3 minus 1 is 2. 3 different social media app preferences. 3 minus 1 is 2. 2 times 2 is 4 degrees of freedom. So we're going to go to chi-squared CDF. Our lower value is going to be that 12.589. Our upper value is going to be 999, acting like infinity. And our degrees of freedom is 4. And we get a p-value of 0.0135. Now, They did ask us to use a significance level of 1%. So we would say since my p-value of 0.0135 is greater than 0.01, I will read fail to reject the null hypothesis. I'm not saying the null hypothesis is correct. I just do not have enough statistically significant evidence to suggest that there is a difference in the distribution of social media preferences across the three populations of middle school students, high school students, and college students. It appears that there is no major difference of social media preferences across these populations. All right. That's it for a chi-square test for homogeneity. Hopefully you see the slight differences. It's mostly in the hypotheses, the null and the alternative, when we compare them to a chi-square test for independence. All right, that's it for Unit 8 on chi-square tests. Again, 3 different chi-square tests: goodness of fit tests, test for independence, and a test for homogeneity. They're all a little bit different. The big change is for a goodness of fit test, there's only one categorical variable, so that's pretty easy to recognize. For the other two, you really got to do a good job of reading the problem and reading the question to decide if it's independence or for homogeneity. But to be honest, a lot of the aspects that go into a homogeneity test or an independence test are pretty much the same, expecting when it comes to finding the expected values, degrees of freedom, calculating chi-square, and all that fun stuff. All right, that's it. Hopefully it was a great quick review of Unit 8, and you'll be ready if any of these questions pop up on the AP exam. See you in the next video.